The first part of today is to finish the discussion from Monday that I tried to cram into 3 minutes. Didn't work at all. Then we're going to just spend today talking through more examples of reduction. Just the more examples you see, the more comfortable you'll get. This is where we kind of left off last class legitimately, right? We saw what a reduction was, and I want to be clear, this reduction we did, there was a question about directions. The reduction is a function that maps strings in or not in HP to strings not in or not in null bar. Okay, that's the sigma. There's a question about the direction because in the discussion of what a reduction gets you, it's the opposite direction. If any of you have seen enough math to know the word contravariant functor, this is what we're talking about. If you haven't, it doesn't matter. The point is, this was the sigma, this was the this whole thing here was the add a zero in the toy example, right? You take an input, which may or may not be an HP, it's a machine and a string, an input string. That's the input in blue. The output is that machine, M prime in green. So it's not a string and a string, it's a machine and a string and a machine. So it's a more complicated concept, but this part is the left to right part. This is the sigma. This is the quote unquote add a zero. It respects being an HP or not. Being an HP or not for the input exactly turns into the output, M prime being in null bar or not. Okay, that's the part up at the top right. Those are the two things you'll have to show for a reduction. You'll have to construct it, of course, and then show those two properties hold. An input in the set in question maps to an output in the set in question. And same thing for the complements, okay? Here's the full statement and context of everything we've seen. The rest of today we'll just work through more examples and think them through, okay? You're given a set A in some set sigma star and a B in some set psi star. The alphabets could be different. Okay, a reduction of A to B is a computable function that takes every string in sigma star and maps to some string in psi star, and the property of being in A corresponds exactly to the property of being in B. X being in A if and only if sigma X is in B. Okay, this is the picture, and we'll see all the direction stuff I was waving my hands about earlier. This is the picture for a reduction. This is written A less than or equal to MB. A reduces to B, the less than or equal to is the correct concept, maybe not the word reduction. Okay? What this proves for us, again, it works against your pre-existing notion of what reduction means. A reduces to B means B is at least as hard as A. This is the better way to think of it. This is the proper wording. I'm sorry, these are at odds with each other in my view. Okay? If you had a Turing machine accepting B, you could take sigma, which is a computable function, and do n afterwards. That's the thing we showed in the box, and you get a Turing machine accepting A. Consequently, if B was recursively enumerable by some function n, right, and you have a reduction from A to B, then A is also recursively enumerable. If B was recursive, if this is a total Turing machine, this will be a total Turing machine, and A will be recursive. These are your two standard conclusions and their contrapositives once and for all. This bit here is exactly the picture for every single reduction you will ever see. This is the one to study, inform it by your examples. Okay? If B is RE, there's a Turing machine here accepting B. This Turing machine accepts A, and therefore A will be RE. Contrapositive, the part we'll actually use. If A is not RE, B can't be RE either, because if it were, A would be RE. The second thing is our main use of these. This justifies our statement that B is at least as complex as A. If B was recursive, if this is a total Turing machine, then take X, do sigma to it, and then apply n. The total Turing machine gives you a total Turing machine accepting A. And therefore, A is recursive. Contrapositive. If A is not recursive, then B is not recursive. Every single time, these are the conclusions of a reduction. Okay? If you know something positive about the B set, the A set has to be at least as nice. More importantly, for our purposes, if you know something bad about the A set, the simpler set, the B set has to be at least as bad. The only thing that will change in any reduction you do is what's the set A, what's the set B, and what's the reduction. And that's what we're going to be practicing. Go over this and make sure it makes sense. And if there's any questions, I think this is the last slide for this deck. This is the general picture of every single reduction you'll ever do. There are details of, depending on the set, what your sigma will be and showing it works. But your set of conclusions are the same every time. Just study that and understand it. We have new technology.
Yeah, just want to clarify. N is the Turing machine or the total Turing machine that you obtain after computing sigma, right?
No. So here's the issue. This came up, I can't remember, it was, I think one of you two asked this. There's a direction issue. Sigma goes from blue to green. Takes the A set and turns it into the B set and takes A's complement to B complement. There are machines happening after that too. So I would say you really should be compartmentalizing your understanding of reductions into two totally discrete parts. One, how do you construct the sigma and show it works? Once that's done, put it in a box. These machines aren't the machines we were talking about before. The M and M prime were little machines. That was just what sigma was doing. These are two new machines, N and H. What it gets you is the same every time. This has almost nothing to do with the details of how sigma was constructed. So really take your work in two steps. This part, if you understand it, has nothing to do with the other work we did, the thing we spent a lot of time on. The taking a machine that was in or not in A and making a machine that was in or not in B. That's the find a reduction part. Once you've found the reduction and shown it works, the same reasoning will apply every single time. And these machines have little to do with the machines we constructed.
So here in this case, like N, we have N and H, right?
You're supposing N exists.
Yeah, because
justifies why it's odd that H exists.
Yeah. But my question is that H here in this case is to run N on X prime. Exactly, which is what the box is doing here.
By the way, just so everyone's clear from yesterday, this blue thing was the equivalent to take a string, add 0 to it, and check it for divisibility by 100. That's how you could check divisibility by 10.
Yeah. My question is, how do we know what H is in this case? Is it always running N?
Always the same thing. Yep. Given the N, that's always the H. This is the part that just boilerplate. The finish to an argument about reduction is the same every single time. Fill in your A and fill in your B. This is what you'll be able to conclude.
And as part of our work, do we need to come up with a sigma that?
Yeah, that's the hardest part. Yeah, coming up with the reduction, showing it works are the only thing that changes from problem to problem. This you can go over as many times as you like. Every time we do a reduction, we'll finish by talking about these conclusions. But this part will not change. The part that you don't see here is how did you get the sigma? And how do you show it was a reduction? That's the only part we're gonna have to practice.
So for the examples that we've been talking about, X and X prime are strings, but really they're like encodings of Turing.
Yeah, and in this case, the X was the thing that was or wasn't in HP. We're trying to abstract that out so you're not working about too many machines at one time. And the X prime was the thing that was or wasn't in null bar.
So in the case of the null bar example, X prime here, N accepts a Turing machine. Or
this is a set of Turing machines, and this is a set of strings M hash Y. It's best to, this is the point of abstraction, by the way, to once you've found the reduction and you've double checked that it's really a reduction, ignore the details and think about this, because otherwise it's a couple layers of Turing machines and it's more than you actually have to think about. Yeah, but absolutely true.
We're always going to assume that we have N.
These conclusions, if B is RE, such an N exists, so such an H exists, so A is RE. That's the same argument every time, yeah. You will never construct the N. You will in principle know how to construct H from N, but that is boilerplate, same thing every time. Yep. So we'll go through this reasoning every time we do a reduction today. But in some sense, what I would say is that long discussion of getting HP to null bar with the reduction is the interchangeable part that will change from set to set. Find the reduction, show it works. Find the reduction, show it works. Your finishing conclusion will always be the same. And the good thing is you just have to know what this says, because it says the same thing every time you do a reduction. And the thing I'll mention final bit, because it was asked about, the sigma goes from the blue set, the simpler one, to the green set, more complicated one. Because of the way the compositions work, the Turing machine on the right goes the other direction to give you a Turing machine on the left. Conclusions run the opposite direction of the sigma. I would say you're really well served to find the sigma, show it works, and just put a box around that, close it, and tuck it away. Once you know it works, here's the reasoning.
How did we say that null bar is RE and not undecidable?
We proved null bar was RE at the very start just by writing a Turing machine down that accepted it. Take a Turing machine, you want to see if it accepts a string or not, run it with time sharing on all strings in sigma star, and if it ever accepts one, accept. That will accept the strings in null bar and will not accept the things that don't accept anything. So yeah.
But isn't that not a proof that it, the reduction proof we did doesn't prove that it's RE.
That's right. So we'll prove that something is RE by finding a Turing machine. The harder thing is to show something is not, and that's what reduction will generally get for us. Yeah. Yep. In fact, almost every use of reduction will be to prove a negative result, to prove a set's complicated. We will know about the blue set, like HP we knew about. HP was RE but not recursive. If we can find a reduction of HP to null bar is definitely not recursive. We had to separately show it was RE. Yeah. The reduction shows that since HP is not recursive, null bar can't be recursive in our example. It might not even be RE. That's a separate proof, totally independent. So the positive proofs, you'll actually construct a Turing machine. Show that it's recursive, show that it's RE. The negative results is what we're after here. That's why this is akin to the pumping lemma. The hard part of all three topics is the negative results. In block 1, it was a pumping lemma for regular sets. In block 2, it's a pumping lemma for context-free sets. In block 3, it's reduction. This is how we will prove sets aren't RE or aren't recursive, by finding simpler sets that aren't RE or aren't recursive and making a reduction. And that's what we're going to do for the rest of class today. It's a lot, but again, I really, really mean this. Take it to heart. The work finding the reduction and showing it works should work completely independently from this boilerplate conclusion that you get afterwards, which really boils down to these consequences right here. The rest of the explanation of why the consequences, which you should know, but when you're doing a reduction, the key facts are these two or really these two. The simpler set's not RE, the more complicated set's not RE. If the simpler set's not recursive, the more complicated set's not recursive. That's the automatic conclusion anytime you have a reduction. Okay? All right, so the rest of our game today is to do some reductions. Here was the picture again. Pictorial representation was, what's the reduction? You've got some set in its complement in some alphabet star. You've got some other set in its complement in some alphabet star. Sigma is going to transform these things to these things. In our last example, it was an M hash Y in or not in HP, transforming to a machine in or not in null bar. It's always the general picture you're doing. What you have to show, you have to do two things. One, construct the new machine, construct sigma. And two, show it has these properties.
So every element that is accepted in A should be accepted in B, but not every element by the two different. But if an element is looping in A, it's okay for it to be rejected.
So the big point is this. We're not even talking at this level about Turing machines. We're just saying in the set or not. How you'd figure out it's in the set, which is something you're legitimately very concerned about, is a totally different question. All we have to show with the reduction is that things in the set theoretically end up in the other set theoretically. And you can justify that. And things not in the set theoretically end up not in the other set theoretically. We're not worried about this being a computation at this point. Just theoretically, does this relationship hold? We're not actually talking about individual Turing machines yet.
The computation that comes later is what proves to us.
Yeah, the computation that comes later. So I'd say this part of what the reduction is, I wouldn't think about that. The boilerplate conclusion in the end is where that comes in. Yeah, absolutely. So I won't hand this next page out yet because I really want you to think these through carefully. And I hate the fact that if I give you a printed handout with kind of the work on it, I'm going to show you the reduction in step 1. And I want you to think a little bit how you might get that reduction first. If you see this one immediately, hold your tongue for a second. Here's how a general reduction is phrased. Here's two sets. HP bar, you're looking at M hash Y that's either not in or not an HP bar. and you want to construct a machine that's in or not in fin. Now, what does HP bar mean? What are the yeses for HP bar? Where M doesn't halt loops. What are the yeses for fin? The machine accepts a finite set. There's only a finite number of strings it accepts. So here's the thought process you should have, and if this seems daunting and impossible, that's kind of okay. That's why we're seeing examples first. You got to be driven by examples you've seen, otherwise this is a really difficult process to think through. If I'm given an M hash y that loops, I want the new machine to accept a finite set. Also be clear there's two halves to a reduction. If I'm given an M hash y where M halts on y, I want to get a machine accepting a not finite set, an infinite set. This turns out to be not a hard reduction. In fact, it's one you've seen before. So we're going to lead in with one you've seen before. Realizing this is one you've seen before is useful. Given an M hash y where M loops on y, you could, in your green machine, think of just running M on y. And if M hash y is an HP bar, that's never going to finish. Doesn't matter what the rest of the code is. You won't accept anything, and nothing is a finite set. Getting HP bar to finite is actually easy. Now, get the second half. If M does halt on y, I want to accept this. If I'm an HP, I need to get a machine that accepts an infinite set. Might as well accept everything. Here's the machine you've seen before. These should look familiar. To get HP bar to fin, it's the same reduction we saw before. So you will see themes come up in these reductions. I'm going to show you several of the themes in our examples. This machine, let's just make sure we're clear, how you might think of it is an imagination process. You have to think about in or not in M hash y, looping or halting. How can I get a machine that accepts a finite set or an infinite set correspondingly? It may take some exploring and trial and error to get a reduction like this, but let's make sure we know how to check it works once you have one. If you find one that doesn't work and you check it, it won't work and you know to try again. If you find one that does work, you'll go ahead with the reduction. Here are the key questions to ask. Okay, there are two cases. The blue string M hash y is either in HP bar or not. There's the yes and the no part. Yes needs to turn to yes and no needs to turn to no in a reduction. So theoretically, not worrying about how you'd in some sense determine this, if M hash y is an HP bar, M loops on y, read what that machine does. Step 1, run M on y, will loop. This won't accept anything. What is L of M prime if M hash y is an HP bar, doesn't accept anything? It's exactly the argument we went through before, so I want to let you see that you may see similar arguments applied again and again. Okay? If L of M prime is the empty set, is the empty set finite or infinite? Finite. That's half what it takes to have a reduction. Now, finding it's the hardest part. Defining a function that does what you want it to do. Taking the M and the Y in this case and putting some words around them to get a new Turing machine is the hard part. If you've made the right choice, it won't be hard to justify these, but this is half of it. Okay? If M hash y is in HP bar, M prime's in fin. In means in. Okay? Don't forget the second half. And you're going to be practicing the definition of these sets a lot. Every single time you use these, you can be practicing your definition of the sets. If M hash y is not in HP bar, then it's in HP. What does it mean for M hash y to be in HP?
Halts.
M halts on y. The first line will run and we'll ignore its result. We will always accept. What is the main question? What is L of M prime now? Sigma star. Just the same reduction as last time, so I want to let you see. You're seeing the same one. Think it through from scratch. You've seen it once already. Okay, it's the same construction both times. The sigma is the words I put around the M and the Y to get this new machine M prime. The same thing to put around the strings takes a machine in HP bar and gives me a machine in fin. And if I take a machine not in HP bar, L of M prime will be sigma star, to accept a finite set or infinite set. So it's in fin bar. That is the two things you have to show to know your reduction works. So reductions are not nearly as bad as the halting problem to show. Hard part, find the machine. Straightforward part, justify if the input is in your set, HP bar, show the output's in your set fin. If the input string is not an HP bar, see what the machine does and justify whether or not the new machine's in FinBar. That's what you need. Okay? In HP bar gave me a machine in Fin. Not an HP bar gave me a machine in FinBar. That's exactly what a reduction is. So I'm running through that one really quickly, but you'll see this theme again and again and again. That's what you need to do. Here's your standard conclusions to run through. I've got a reduction. I've shown you. There's the function. I've checked the two things I had to check. That's your main work for a reduction problem. Make sure you know how to finish the conclusions off. What does it tell you in terms of less than or equal to relation about HP bar and Fin? It's not bad to write it down. It may help lead your intuition. HP bar, I hate the word reduces to, less than or equal to Fin makes it sound a lot more like it should. HP bar is no harder than Fin is. Alternatively said, Fin is at least as hard as HP bar. Now, what do you know about HP bar? Well, the HP was what? These are your poster children in block 3. HP was RE but not recursive. HP bar was not recursive. Negative statements about the simpler set give you negative statements about the complicated set. Positive statements about the complicated set give you positive statements. I don't know anything about Fin yet. This is our first fact about the set Fin. Not recursive. If the simpler set's not recursive, what can we tell about the more complicated set? This is the boilerplate. All that thing was the justification why this reasoning works. This is the same easy reasoning every time. The hard part is getting the reduction showing it works. That's what we're going to practice. Not recursive. That is our first fact about the set Fin. Fin is not a recursive set. Now, if you think about your Venn diagram, it could be
RE or co-RE.
It could be RE. It could be
Co-RE.
Yeah, it could be RE or it could be core. It could be neither.
Yeah.
I mean, I guess we could say more. What's the other thing you know HP bar is not? We've justified this. We actually know 2 negative statements about HP bar. HP was not co-RE, so HP bar is not RE. We could have done more. HP bar is not recursive. It's also not even RE. It was purely co-RE because it was co-RE but not recursive. Consequence, if the simpler set is not RE, Fin is also not RE. That's an even stronger statement. So 2 things we know about Fin. It's not recursive because it's not RE. Now what's left of this? In terms of the 4 possibilities, it could be both and recursive. It could be just RE, just co-RE, or neither. What are the possibilities that are left of a set that's not recursive and not RE?
Co-RE or
It's co-RE or neither. Great. I would like to show you that Fin's a very complicated set. In fact, you'll be your first example of such a set. It's not even co-RE. Okay? How might I show that? Reduction. Can you think of a set that's not co-RE that I could reduce to Fin? Just HP. Okay? I'm going to do HP bar to Fin bar, which is equivalent as HP to Fin. I would suggest you don't look at these boxes. This is the second page by now, so I can safely hand out the first page. Okay? Don't look at these boxes and think about them. This is a much harder question, and it may seem like it's not even possible at first. If you like, by the way, this is equivalent to saying HP to Fin, if you like. What do I need for a reduction from HP bar to Fin? To Fin bar, yes, HP bar to Fin bar, HP to Fin, sorry. Can I use my trick of running the machine and then accepting? No. If my machine looped and I run it, I won't accept anything. That's not an infinite set. I need looping to turn into an infinite set accepted. I need the opposite of last time. I need not looping to turn a finite set accepted. This is the opposite of the last reduction. This is not the reduction you've seen before. This one is not nearly as easy, but the point is, maybe to stew for a minute on why this seems difficult, but then come up with a way to prove it anyway. And once you've seen that technique, this becomes something to add to your toolbox, ways that you can form reductions. Is everyone clear? If I want situations where the input loops, to map to machines accepting an infinite set, I can't just run my machine. If I run my machine and it loops, I'm not going to accept anything. That's not an infinite set. The last reduction won't work. This is slightly more complicated. I mean, you can always look at the second page. I don't want to spend too long thinking about this, but okay. Oh, sorry. Good catch.
Wait. We're trying to prove that fin is not co-RE, right?
Yeah. Well, we're going to prove finbar is not RE. Same thing. Oh, you have a guess? Okay, yeah.
Can you do like something with time sharing with after each loop you accept a string?
You have to somehow use your input. If you're doing a reduction from HP or HP bar, you're given a machine and a string. That's the only string you know about. You're always going to run M on Y, but how is the question? And one step at a time is part of the answer, yes.
So like after each step, accept a string, so that if it runs forever, you're going to accept infinite strings, but if it stops, eventually you're going to accept finite strings.
That's the right idea. I mean, that might be similar to what Toby was going to say.
Can you step through M hash Y and then only accept if like the number of steps is greater than the length?
That's another way to do it. So this is the standard construction because it looks a lot like the last one with one small difference. I'm going to run M on Y. It's the only thing you'll ever do on a reduction from HP or HP bar. That's why these are a little bit the easy ones. You've got an M and a Y. The only thing to do is run M on Y. We're going to need to use the input of my green Turing machine now. Whatever string I'm given, I want to accept an infinite number if my blue machine loops. I can let my string determine how long to run the machine. I run M on Y for whatever my input string was, is length, number of steps. Okay? If it hasn't halted yet, accept. Now, seeing that that is the correct construction amounts to showing two things. Now, again, coming up with this idea, a few people had ideas that are on the right lines. If you didn't, that's fine. I don't expect you to come up with a way of using an input that you've never seen before on the exam. But this one works, yes.
Quick question. Why do we know that if we run it for like the size of X, that it will actually continue to loop on Y?
Well, here's the point. Let's go through it very carefully. So regardless of any of the context, there are always two things to show for a reduction. One, if your input's in HP bar, you want your output machine green to be in fin bar. Let's just do them one at a time. It's always worth splitting cases and not trying to think through the machine in general. Okay, case one, read that green machine when M hash Y is in HP bar. This is the easy half. What does M hash Y in HP bar mean? M loops. Now here's the key thing. It's one M and one Y, whatever X is fed in. At that first line, run M on Y for absolute X steps, length of X steps.
Will not accept by then.
It can't have halted because it's never going to halt in this case. In case one, M loops on Y. The first line will not have halted after any number of steps. That's what looping means, and therefore you'll accept. What strings are accepted? Sigma star again. Now notice, simply running M and Y and accepting was going to accept on a looping machine nothing. I've done the opposite now. By a clever running of the machine, when M looped, I'm going to accept everything. Okay? Now, quick conclusion. If L of M prime is sigma star, and you want to explain Y in words, the Y is M loops on Y, it will never have halted, so you're going to accept everything. It's a very short reduction machine. Now, easy question. If L of M prime is sigma star, is that a finite set or an infinite set? Infinite set. That's the first half of reduction. Coming up with the function's the hard part. Okay? This is the easy half of showing the reduction works. Remember, there's two halves though. Okay, so moving forward, the other thing you'd have to show, the double negative is just something to practice here. If M hash Y is not in HP bar, that's the other case, you want your machine, the green machine, to not be in fin bar. Well, M hash Y not in the complement of HP means it's what?
Wait, what, sorry?
M hash Y not in HP bar means M hash Y is
Will halt.
in HP actually, right? Not in the complement means in the set. So M halts. Something you'll find useful for your arguments. For a machine, this will come in several cases throughout the rest of the class. M halts in some number of steps. Let's say the number of steps is K. Okay, it's useful to say if your machine halts, there's some certain number of steps until it halts, and that's going to be important for this argument, so let's give it a name. K is the number of steps it takes for the machine to halt. And by the way, I know it halts at some point, it's in HP. Count the number of steps. That will let you answer the following question. Which strings will be accepted by the green machine? Well, I'm going to run M on Y, this thing, which will halt after K steps. Now the question is, which comes first? K steps and I've halted, less than K steps and I haven't. M prime accepts which strings? Accepts X, if and only if. You can guess it's a relation between X and K.
Yeah. If X is bigger than K. Bigger or equal.
Yeah, it accepts, if it hasn't halted, it accepts only if absolute X is less than K. On the K step, the machine halts. So K's 10, just say for example, if K were 10. Any string of length less than 10, it won't have halted yet. On the strings of length 10 or more, it will have halted. The strings that are accepted will be specifically exactly the strings of length less than K. L of M prime is the set of all X in sigma star, where the length of X is less than K. That's a finite set. This is only the second half of the reduction, you're done. What set is M prime an element of? Fin. That's the second half. Now, it takes a slightly harder reduction. In the looping case, you get a cleaner argument. And in the halting case, you have to be a little bit careful. But you can tell me, for a given M and Y, where M halts on Y, right? Not an HP bar means an HP. Name the number of steps. It only depends on M and Y. It will halt after some number of steps. Useful to give that a name. Given that K, you can read that machine and tell me exactly what strings will be accepted. Find L of M prime, and once you've found it and justified why that's the case, check what set your machine is in. I found that if M hash Y was in HP bar, the new machine M prime was in fin bar, and if M hash Y was in HP, my new set was in fin. That's a reduction. Yeah.
Oh yeah, I mean like for the K, like
Yep.
are we like K should be different for every single.
This machine is now actually reading its input string for the first time in the course. The green machine has an X. Every time so far we ignored X and just did some stuff with M and Y. Now, depending on the length of X, that tells me how many steps to run my machine for. Right? If it hasn't halted yet, I'm going to accept it. And at length K or more, it's going to halt and I'll reject. That pins down my accepted strings to the short ones.
Yeah, I just thought for every X like running in the machine M, the number K should be like changing. It's not like always like a constant.
Well, here's the key thing. For a given M and Y, that's the machine independent of what, so here's, maybe that's the point. I'm running M on Y, not X.
Oh.
M came with a string to run on, and for that string, no matter what X is, running M on Y will halt after the same number of steps every time, and that's important.
Oh, okay, I gotcha.
Be very careful. When you're handed a machine and a string, you're always going to run the machine on the string. Your green machine will be given a different string, and you're allowed to use that string any way you like. And this is a useful way to do it. If you get this one, this is the next most difficult reduction. By the way, Wednesday is 2 more reductions. It has a name, those 2 reductions, but yeah.
I'm just trying to understand like a basic process. I don't get this confused anymore. So X is obviously a part of the infinite set. And so when you say run M on Y, what exactly is Y?
At the very start, the sigma takes an M hash Y, a machine and a string, and I know in this case that the machine halts on the string. And for that M and Y, that green thing in the box, the machine I built, it has the M and the Y hard-coded into it, and any string X it's fed, it take any string for input, right? I can let the string that's input dictate how many steps I run M on Y for.
I see. So Y is just like an arbitrary string that...
Y is the string you were given, and M's the machine you were given. This is a very good point. In these arguments, all you know about, do the 2 cases separately. In the first case that M hash Y was an HP bar, all you know is that M loops on Y, and that was enough to make a conclusion. In this case, for a given M hash Y, there's exactly 1 M prime, and I know that that M and that Y halts after K steps, and I can use that somewhere. That this will still take some reading through to understand it, maybe several passes on all of these, But the goal is after today, you're prepared to go through and read these and understand how they work. Yeah, good. That's our second reduction. Now, this is cute. I mean, it's more than cute. I guess it's interesting. I guess interesting is better than cute. So what's the conclusion? Same boilerplate conclusions every single time. Be careful. What would you write down if we do a reduction from HP to FinBar? And I really think it's important because of the word reduction to get the word out of it. I will rarely say that. HP bar is smaller than, in a machine sense, FinBar. Great. Don't let the word reduction confuse you. Again, the green set's the harder one, the blue set's the easier one. What do you know? What's the negative facts about HP bar? It was not recursive. Why? It was not RE. Automatic conclusions. Negative stuff from the simpler set transfers to the complicated set. FinBar is also not recursive. Why? Because it's also not RE.
Oh, no, no.
No, HP, yeah, so be careful. This is the opposite proof of last time. The easy set is not RE, HP is RE, HP bar is not. FinBar is even worse. If HP bar is not RE, FinBar isn't RE. Now, you may be jumping ahead. We saw earlier, I can't spell earlier, sorry. Writing and talking at the same time doesn't always work. Earlier, our previous reduction, you can flip back on your page, said that Fin was not RE. Okay, here we've seen that FinBar is not RE, so Fin, if a set's not RE, its complement is not co-RE. Therefore, Fin is not RE and also not co-RE. Fin is your first example of a set that totally escapes our adjectives. It's not recursive, it's not RE, and it's not even co-RE. It's that outside part of the Venn diagram. It's your first set that goes in that box. Okay? We have to do 2 reductions to show it, right? One reduction showed that it wasn't RE, and the other reduction showed it wasn't co-RE. Huh?
And we know it's not.
We know, well, if it's not RE, it can't be recursive, actually. So technically speaking, all my conclusions, the not RE is a stronger statement than not recursive. Yeah, so it's not recursive, it's not RE, it's not co-RE. It's in that outside undiscovered country, which is the first thing we'll talk about after the exam. It turns out there's a lot of sets that aren't RE or co-RE. We will see why on Wednesday, some argument why, and we'll kind of put some order onto that situation the Friday after the exam. This is your task though, so understand these reductions. That's our first set we've justified. Maybe that's your poster child for a set that escapes all of our adjectives right now. It's not recursive, it's not RE, it's not co-RE, but it's a perfectly fine set. Fin is a set of Turing machines. It's the ones that accept a finite set. By the way, what can you tell me about FinBar automatically? If Fin is neither co-RE nor RE, its complement, same, also neither co-RE. So we've already come up with 2 sets that are neither RE nor co-RE. They've escaped all analysis so far in the course. And we can prove that, okay? The last 2 sets are more complicated still. Another really complicated set, you might guess that checking whether a Turing machine accepted a regular set should be even harder than helping it accept a finite set. Regular sets are more complicated than finite sets. Before we even start, remind you of stuff from block 1. You all know of a lot of non-regular sets. The poster child was A to the n, B to the n, or maybe 0 to the n, 1 to the n to keep it in binary, right? Is everyone okay that this set X is not regular? Back to block 1. It is context-free, but it's not regular, right? No stack you can't possibly, because you could do the pumping lemma on it for regular sets. This is this is your poster child for a non-regular set. However, I hope it's obvious to see it's not that complicated. You could write a total Turing machine accepting it, actually, right? In your Python program, total Turing machine, read the number of zeros, count them up, read the number of ones, count them up, return true if they're equal. Easy. Okay, so this is a set that no finite automaton could accept, but of course a Turing machine could. For this next discussion, I need an example of a set that's recursive. I mean, RE is enough, but recursive, but not regular. Okay? Here is our reduction. Again, don't flip ahead to the page if you want to spoil the thought. I'm going to show you that reg is also the set of Turing machines accepting regular sets is also not RE or co-RE through the same means. How might you, if you think this through, construct your reduction? Well, if it's HP bar to reg, what I want is a yes means a yes. If I've got an M hash Y and HP bar, what does that mean about M and Y? It loops. I want my new machine to return a regular set. What's the simplest regular set you know? The empty set. So it seems like running M on Y, the easy thing from the first examples, is going to work here. What if M halts on Y? What if I'm in HP, the complement? I want a machine that accepts a non-regular set. Do I know any machines on the screen that accept a non-regular set? K. Just do K. This one isn't too hard to think about. This is the easy one of the next two. We're going to do a pair. HP bar to reg and then HP bar to reg bar, a little bit harder. This one's not the hard one. If you're given a machine and a string, when the machine doesn't halt, you're going to run the machine. If you ever want a yes to mean the empty set for HP bar, just run it. Can't accept anything because you'll never get to the second line. Okay? If M hash Y is an HP bar, M loops on Y. Therefore, this step will never finish. L of M will be the empty set. Quick question, if L of M prime is the empty set, is the empty set regular or non-regular? Back to week 1. It's a finite set. All finite sets are regular. That's my first half of a reduction. If M hash Y was in HP bar, yes. My new machine was in reg, yes. Yes.
Why do you need to run M on Y? Can't you just run K on X?
If we did, I wouldn't pay any attention whether M looped or not. What I need is that when M loops, I accept a regular set.
Yep.
So I can't afford to run K on Y and return its result because it will accept a non-regular set. So this first line is kind of like a stopper that says, well, if my machine, it's easy. If your machine loops, run it, you'll accept the empty set because you'll never get to the next line. Whatever the next line says doesn't matter, right? And that gets you half of this very, very cheaply. Again, if you want a looping situation to give you an empty set, that's easy to do. Make your first line to be run M on Y. It's easy. Next lines don't matter. Yeah.
And we can have K to be any Turing machine that accepts a non-regular set.
We just need any non-regular set and any Turing machine accepting it just to get the second line to run right. We need to engineer our machine M prime to, well, let's do the example. Let's get the second half, as long as you're clear with what the first half says. If M hash Y is not an HP bar, again, practice our terminology very carefully. M hash Y not an HP bar means M hash Y is in HP. Therefore, M halts on Y. And this is not the hard reduction. If it halts on Y, in this case, that first line will finish, and I'm going to ignore the result. I'm going to run K on X returns result. L of M prime will be just the same as L of K in this case. And L of K is
Non-regular.
X, and X is not regular. So M prime will be in reg bar. So I can engineer, given a M hash Y, if the M loops on Y, I just run it and I automatically accept the empty set. If M doesn't loop on Y, I run it and then just let K answer the question for me. K will accept by definition a non-regular set. I will accept the same non-regular set. My machine will be in reg bar. Esdras.
Yeah, I was going to ask about engineering M. So you can engineering M just to answer the question that you have.
You're trying to make an M that, depending on whether you're in or out of the blue, this will be in or out of the green. And that's an exploration, it's an invention process, so it's hard.
Do you also, could you also say that you assume that there is always going to be a Turing machine that accepts M hash Y, and then you can construct M prime so that
well, I'm not really using the fact that HP bar is or co-RE or RE or anything else here. This is just the construction of the reduction. right? I don't care about anything about HP bar or reg yet. All I care is what the strings in them are. What I need is things in HP bar, this new machine, it gives me a machine in green that's in reg, and things not in HP bar give me a machine that's not in reg. That's all I need to check for the reduction. So I'm not worried about checking HP bar or anything. I'm gonna be given, for this function, an m hash y. It's either in HP bar or not. I have to make sure my new machine does the corresponding thing. But I'm not worried about HP bar in any other way. I'm just using the fact that being in HP bar meant the first line looped, and being not in HP bar meant the first line halted, and that buys me the two behaviors I need.
Yeah, this was like, so you engineer your m prime so you just so as it matches your constraint. I mean, okay.
You're looking at the blue set and the green set to find a sigma that does the job exactly. Yeah, you're turning a behavior of one machine into a behavior of another machine. Yes.
Could you get rid of k and just do like run m on y, then run m on x and return its result?
Well, you can't run. M is, you don't know anything about M. This is the key thing. If you're given m hash y and you're told it's not in HP bar, it means it halts. But key thing in this context, you don't know what M actually returns, accept or reject.
Oh, it could be regular.
It could be a regular set, exactly. Yeah. So
We need only non-regular output.
yes, we need our machine to somehow accept a non-regular set, and that's why we just chose a non-regular set and a Turing machine accepting it just to get going.
But you could also, this is, I guess, is syntactically cleaner, but this, you could still do something where like, it's like run m on y, and then within the green, just explain like, check that it's a palindrome.
Or some, you could have, I think it's cleaner to do this, but you could have checked whether X had prime length or something and accept, so something else. But this is cleaner, it's a little bit standard thing to do. Also, you'll see this context used, this construction used a couple times. All right, so there we go. So HP bar reduced to reg. We're practicing the same reasoning again and again and again today. Okay? What does this reduction tell us in terms of symbols? I think this is always worth writing down because the symbols kind of don't lie to you like the word does. HP bar is not as bad as reg, or better said, reg is at least as bad as HP bar. Well, we've talked about HP bar several times, won't bother belaboring this point. HP bar is not RE, also not recursive. So what does that tell us about reg? Not RE. Reg is either co-RE or neither RE nor co-RE. It's like in the one moon or nothing. Can't be RE. Can't be RE, can't be recursive. So last example before we get to the weird one. We'll see some really weird ones on Wednesday. HP bar to reg, sometimes they're easy, sometimes they're harder. Expect that when you're doing HP to one set or HP to its complement, one of them might be harder. By the way, the same disclaimer applies. This is equivalent to saying HP to reg. If you have a reduction of A to B, it's the same as the reduction from A bar to B bar. If you'd rather think about it that way, you can. Can I use my previous reduction? It's the opposite of what I wanted. If M looped, it gave me a regular set, and if M didn't loop, it gave me a non-regular set. I want the opposite. How can I make this work? Well, it's actually the same trick as last time, so I'm trying to teach you a trick with these examples. Very similar to the last one. I'm going to run M on Y. I'm only going to run it for as long as a certain number of steps. Okay? I'm going to reject if it halted, and otherwise I'm going to run K on X and return its result. So the first two lines are different, the third line's the same. I'm still using K to somehow accept a non-regular set. This is a little bit messier of an argument. Let's see if we have time to get it. Okay, we'll try. Think this one through. I might rush through this since we can get the next one done before we go. Suppose M hash Y is an HP bar. This is the easy one. If M hash Y is an HP bar, what does that mean? Yeah, this means M loops on Y. Read your machine. Run M on Y for length of X steps. Okay?
Then we'll get to the next.
You'll get to the next step. You reject if it's halted. Has it halted?
No.
No. You'll get to the third line. The third line will run k on x and return its result. What will L of m prime be? It'll do exactly what k did. It'll be x. Sneaky. A looping machine run for any number of steps you like won't halt. So run it and see if it halted. If it didn't halt, which it won't in this case, if m hash y is an HP bar, m will loop. That first line will never halt. The second line you could ignore because it won't have halted. You simply run k. In this case, you simply run k, you get x. Is x a regular or non-regular set? Now, suppose m hash y is not an HP bar. You've seen this argument enough times already. Our practice set is HP bar and HP to begin with. To not be an HP bar means m doesn't loop on y. And I will kind of be specific here. That means m halts on y. And again, this is good for later in the class. If you know a machine halts, there's some number of steps after which it halts, and that'll be useful, because the if it hasn't halted will be important to analyze. Now, what's L of m prime? Think through that machine in the case with the given knowledge that m halts on y in k steps. You're going to run m on y for absolute x steps, so I'd say there's two cases. Given an x is less than k in length, or x is greater than or equal to k in length. Now, if x is less than the number of steps it takes for m to halt, I won't have halted, and therefore I'm just like the looping case going to get to the third line. Okay? If x is less than k in length, I'm going to run k on x. Crucially, if x is length greater than or equal to k, I will run m on y for length of x steps. The number of steps I'm running it for is at least as many as the number of steps where it halts. I'm going to reject. Now be careful. What strings will be accepted by this machine?
The one that loops.
Well, there will be no looping.
It's going to be the first case.
It's the first case that I'm going to reject all the strings longer than length k. I'm going to reject some of the strings of length less than k. This is a finite set. I don't care. It's going to be the set of x in my non-regular set. Oh, x, I guess. The length of x is less than k. If the length of x is more than k, I'm going to reject. So it's going to be the strings in my non-regular set, be careful, whose length is less than k. That's a finite set. It's regular. Finite sets are always regular. So if you chop off a non-regular set at some length, it's going to become a finite set, which is regular, and that's the trick here. This is a reduction, right? So you have a record of this on your sheets. But what do we say? Well, maybe I'll let you fill this out. You know it. HP bar is less than or equal to m reg bar. HP bar is not RE, so reg bar is not RE. Obvious. We've given two reductions, HP bar to reg bar. One tells us that reg can't be RE. One tells us that reg bar can't be RE. Conclusion, reg, both of these are neither RE nor co-RE. So you now have two poster children for sets outside our scope right now. We're going to put them in categories later. Fin is neither RE nor co-RE. It's in that unexplored wilderness. Reg and its complement are in that unexplored wilderness. The way we can show all those facts are via reduction.
Does this mean that you can't have a Turing machine that says whether a set is regular?
If you're given a machine and you want to ask the question, this machine, the set of strings it accepts, is that a regular set? There's no Turing machine that can consistently answer yes or no. It's an impossibly hard question to be given a machine or like a program and tell if the strings it accepts is a regular set or not. That's what we've proven. Yeah, absolutely. 2 minutes. This one I'm going to have to compress, but it's the easiest example of reduction you'll ever see. But it's cute. This is Toby's question from earlier. This is MP. It's very much like HP. The set, it's a machine hash a string where M accepts the string, not just halts on the string. Very similar to HP. You can prove that MP is pretty much that you can do reductions of MP to HP and HP to MP. Not doing that today. The cute thing is that any recursively enumerable set, if you give me a Turing machine accepting that set, which by definition there is if it's recursively enumerable, right? Recursively, an RE set has a Turing machine accepting it. you can actually reduce A to MP. And it's a really silly argument. I'm going to let you think it through because it's simple. I just want to show it to you. You can read through all of this. I don't want to belabor this. We're out of time. Think through the last example yourself. It's the simplest reduction you'll ever see. There it is. Blue is Y. Green is M hash Y. Use the information on the first line to answer these questions. I'll leave that one for you guys because it's the easiest of the lot. Please give reduction careful thought. You will need to do some reduction on the exam. We've seen a lot of reductions from HP or HP bar. Think about how reduction might work for other sets. When it comes time for the exam, I will give you some lists of sets that could be the A or could be the B to think through. Those are the ones to prepare for. I've said most of what I'm going to say. I'll put a discussion up for reduction questions, actually, so you can ask them there, and we'll see 2 more reductions on Wednesday. Keep on grinding on this stuff. You've seen 6 or so examples of reductions. Study the general idea and the conclusions like we saw today. Study the tricks you use to make your reductions. That's the material to be studying. It will take time. Please start it now. Don't do it the day before the exam. You won't learn reduction in one day.